Okay, so in the last video we talked about a fundamental question, which is how does real three-dimensional space that we live in correspond to this two-dimensional complex vector space within which a qubit sits? Okay, and so somehow answering this question is really important if you want to manipulate the state of a qubit in our three-dimensional real space. So it turns out, mathematically at least, there's a very beautiful answer to this question, which comes from this so-called Bloch sphere representation of a qubit. So let's see what that is. Okay, so what that says is something very simple. It's built on something very simple. What it says is the state of a qubit can be represented in terms of two parameters, theta and phi, in this way, where theta is an angle between 0 and pi, and phi is an angle between 0 and 2 pi. Okay, so the state of any qubit can be written as cosine theta over 2, 0, plus e to the I phi sine theta over 2, 1. Okay, so let's see why this is the case. So what's the state of a qubit as we know it? Well, it should be alpha 0 plus beta 1, where alpha and beta are complex numbers and they are suitably normalized. Okay. Now, remember there are two ways we could write down a complex number. So a complex number sits in the complex plane, right? And if we are given a complex number alpha, we could write it as a plus ib, or we could also write it out as in its polar coordinates by specifying the magnitude of this complex number. So let's call that r, and the angle phi. So alpha equal to a plus ib, but it's also equal to r times e to the I phi. Okay, so let's write out this complex number in the r phi in its polar coordinates. So this is, let's call this r sub 0 e to the I phi sub 0 plus r sub 1 e to the I phi sub 1. Okay, now let's do one more thing. So where r sub 0 and r sub 1 are non-negative real numbers. So now let's pull out e to the I phi sub 0. So we get r sub 0, 0 plus r sub 1 e to the I phi 1 minus phi naught 1. Okay, now let's realize one more thing. The fact is that this overall phase is physically irrelevant, right? If we make any measurement on the system, this overall phase is not going to make any difference at all, so we can drop this from consideration. So now to describe this quantum state, we have this parameter phi, which we'll call, phi 1 minus phi naught, which we'll call phi. And then we have these positive real numbers, r naught and r1. But remember, we have a normalization condition, so r naught squared plus r1 squared equal to 1. And so equivalently, we could write r naught as cosine theta over 2. Well, we choose theta over 2 for reasons that will become clear in a minute. It's just cosine of some angle. And r1 would then be sine of theta over 2. And so now you get exactly this representation that we mentioned earlier. Okay, so what's the net effect here? What we're saying is, really there were, you'd imagine, here's another way to think about this Bloch sphere representation, this representation of a quantum state. We're saying Well, a quantum state is represented by two complex numbers. A quantum state of a qubit is represented by two complex numbers. You'd imagine that there are four real parameters that you need to specify this state. But on the other hand, one of the parameters doesn't matter, which is the global phase. So you're left with three parameters. And then there's one more parameter that you can get rid of because of the normalization. So you have this constraint alpha squared plus beta squared equal to 1. And so you can really describe this system with two real parameters, and those are theta and phi. Okay, so now let's try to picture this quantum state in three-dimensional space. And this is what the Bloch sphere representation does. So what we think of, the way we think of this vector psi is as a unit vector in three-dimensional space, where theta and phi are our polar coordinates in three-dimensional space. So in other words, we are thinking of three-dimensional space where these are x, y, this is the x, y, and the z-axis. So the z-axis points up, x and y like this. And now we can specify a vector by specifying its length, in our case it's 1, and then specifying the polar angles. So the angle theta is the angle that this vector makes with the vertical, with the z-axis, and the angle phi is the angle in the xy plane. So it's the angle that its projection makes in the xy plane. So once you specify phi and theta, you've actually specified a vector on the surface of the unit sphere in 3 dimensions. So wait, what are we saying here? What we are saying is, instead of thinking of a qubit as sitting in a 2-dimensional complex vector space, on the unit sphere in a 2-dimensional complex vector space, we can equivalently think of the state of a qubit as sitting on the surface of a unit sphere in 3-dimensional space, where we specify it, by two parameters, theta and phi, the polar angles, and then the state of the qubit would look like this. Okay, so let's now go ahead and orient ourselves in this space. So what does the positive z-axis, what does this correspond to? What state of the qubit is this? Well, this corresponds to theta equal to 0, phi equal to 0, let's say, which is just the state. This is also the 0 state. What about the state minus z? Well, this corresponds to theta equal to pi, which means theta over 2 is pi over 2. And so now what you would get is this state is a state equal to 1. So here's something interesting. So in our complex vector space, 0 and 1 were orthogonal states. But once we represent them on the Bloch sphere, they are actually antipodal states. They point in opposite directions. That's where this theta over 2, this factor of 2 comes in our representation. Okay, what about the x-axis? What state does it represent? Well, for the x-axis, we have the x direction, we have theta is equal to, so now our angle with the vertical is pi over 2, and we are assuming phi is equal to 0. And so what it represents is cosine pi by 4, so which is 1 over square root 2, 0, plus 1 over square root 2, 1. So it's just the plus state. So x, the state pointing in the x direction, is the plus state. What about in the minus x direction? See if you can work that out. Okay, let's work out also what's the state pointing in the y direction. So in the y direction, we have theta equal to pi by 2 and phi equal to also pi by 2. So cosine theta over 2 is cosine pi by 4, again 1 over square root 2, 0. But now we have e to the I pi over 2. Right? What's e to the I pi over 2? It's just I. So you get plus I over square root 2, 1. Okay, and again, you can figure out what's the state that points in the minus y direction. Okay, so make sure that you orient yourself on the Bloch sphere and you play with it to understand, what states are pointing in which direction.